Hi, I'm Antonio, and I'll talk about our paper, Variational Objectives for Markovian Dynamics with Backward Simulation. This is joint work with Zijia Wang, Luhan Wu, Ido Drori, and Itzhak Pierre at Columbia University. Hidden Markov models formalize a set of ordered discrete time measurements that are taken on top of a latent dynamical system. We're often interested in two distinct tasks. The first is to infer the latent trajectories and the latent dynamics that govern those trajectories. And then the second is to learn the transition and emission functions from the observation sequence. We're particularly interested in this problem when the latent trajectories are continuous and the transition and emission functions are nonlinear, which is a source of intractability. Recent connections between two families of approximate Bayesian inference algorithms, variational inference and sequential Monte Carlo, have been established, where sequential Monte Carlo is used to construct an estimate of the marginal likelihood, which is then used to define a variational objective by forming a lower bound. These objectives are filtered, meaning that the estimate for the latent state at time t uses information only up to the current time point, as opposed to the complete observation sequence. Filtering sequential Monte Carlo operates on a sequence of probability spaces. The idea is to decompose the problem across time steps, define a tractable proposal distribution, draw case samples from that proposal distribution called particles, and then compute the ratio of target distribution to proposal in order to calculate importance weights. Repeating this process, we see that it's useful to resample particles based on their importance weights to focus the computation on areas that correspond to high probability mass. Iterating over time steps. Variational inference is a technique that approximates an intractable integral of a distribution P with a tractable distribution Q, and in doing so, fitting the parameters for Q and P trade integration for optimization. We'll exploit a hidden symmetry whereby minimizing the KL divergence between Q and P is equivalent to maximizing a lower bound called the elbow. We also may want to parameterize both Q and P, proposal and target, using neural networks instead of hard coding these parameters, and then train both the proposal and the target in the style of autoencoding variational Bayes or in multi-sample objectives like importance-weighted autoencoders. Weighting samples by this ratio of P over Q in essence corrects for our approximation by biasing the proposal towards the true posterior. Sequential Monte Carlo constructs a filtered estimate of the likelihood and an objective. And this estimate is biased for the log marginal likelihood, where the bias decreases as the number of samples increases. Smoothing has existed in the literature for some time. An algorithm forward filtering backward simulation by Godsil proposes this smoothing posterior, where samples are drawn from a continuous proposal in the forward pass, and the backward pass only performs a discrete resampling, which is akin to throwing darts in the forward pass and only reweighting those darts in the backward pass. This limits the expressiveness of a variational family that can be potentially defined using the FFBSI algorithm. So can we design a smoothing posterior that uses a continuous domain backward proposal based on the smoothing posterior from Godsil? Well, we want to design our proposal to approximate our target using self-normalized importance sampling. So we'll subsample subparticles and compute subweights, and then select a subparticle index with probability proportional to the subweight. And this will yield IID sample trajectories and a smooth variational objective. In a bit more detail, here's a continuous domain backward proposal, which factorizes Markovian. We'll sample M subparticles for each particle, and then use these samples to define subweights, where the weights are proportional to this ratio of target to proposal, which is smooth. And this heuristic facilitates smoothing the target as well as the proposal when you train the parameters of target and proposal by pulling the target towards the proposal, which is smooth. Finally, we can construct a standard estimator and smooth variational objective. And our proposal factorizes across time points, and we can prove that this gives an unbiased estimate of the marginal likelihood. Well, how should we evaluate model performance? Well, any generative model for nonlinear dynamics should be more than just a good autoencoder. The elbow is not a performance statistic that generalizes across models, especially across different generative models. And furthermore, the hidden trajectories connected by smooth transformations can result in equivalent representations of the data. So we want to focus on topological features of the dynamics, and we want a quantitative way of evaluating our performance that must be based on the observation sequence. So the idea here is a statistic called the k-step mean squared error, where we repeatedly apply the transition function and then apply the emission function a number of times over a rolling window of the data, and then compare the predicted observation sequence and the data sequence. And we can compute mean squared error and a normalized version in R squared, k-step R squared. So let's take a look at some nonlinear dynamical systems. Our first example is the Fitz-Unigumo model, which is a system of two coupled differential equations with a cubic term and a linear term. So we'll integrate the Fitz-Unigumo system over 200 time bins with random initial points denoted by markers. We'll then take a one-dimensional observation on top of that 2D system to form a partially observable system, which is of interest in a lot of use cases. So here our observation is just the first variable. It's just Gaussian noise on top of the first variable. So it's important to note that filtering can't infer the initial point correctly from a 1D observation, and you can see this by projecting, by fixing a dimension and projecting the marker onto the plane, and just noting that you won't be able to tell whether or not you're inside or outside the limit cycle. So the center plot are the inferred hidden trajectories and the dynamics, which are topologically similar to the ground truth. And we see the algorithm across training epochs here. So initial points are located correctly both inside and outside the limit cycle. Finally, we can look at this k-step R squared to show that we get perfect k-step R squared at 30 steps. And our method is outperforming filtered variational objectives and a variational inference technique for linear dynamics on top of nonlinear emissions. Now let's look at the Lorentz attractor, a system of three coupled nonlinear differential equations with chaos. So small perturbations in the initial point give us different trajectories in phase space. So let's define a 10-dimensional nonlinear observation on top of this 3D system to see if we can perform dimensionality reduction effectively and learn dynamics effectively. So the leftmost plot shows the smooth inferred trajectories. The center plot shows the elbow value as the number of particles and subparticles increase, and we get tighter bounds as both K and M increase. The right plot shows the k-step R squared value, and our objective, LSVO, is consistently outperforming filtering variational objectives with a smaller number of particles. So variational inference is a trade-off between tractability of the variational approximation and expressiveness of the generative model. If the variational family is limited, then when we train both theta and phi, we can pull theta towards phi. One technique to deal with this is to share the transition function between the proposal and target given the model architecture. So here we look at convergence when sharing the transition function, which is a nonlinear function of latent space, psi, between proposal and target. So the center plot shows the convergence when training separate functions for proposal and target. And what we see is that smaller number of samples, the number of samples converges slower to a lower objective. And highlighting this point, we can compare for 16 samples, the faster convergence to a higher elbow value when sharing parameters. Finally, let's look at electrophysiology data downloaded from individual neurons of mouse visual cortex from the Allen Brain Atlas. So these are experiments where both ends of a cell are clamped and hit with an input current, and we record the voltage inside of the cell as it spikes. So here are two examples of 30 trials downloaded from the Allen Brain Atlas. Here we plot the 10 millisecond prediction on top of the data, and we see that our smoothing variational objective is able to capture the depolarization and hyperpolarization nonlinearities in the data. Finally, we can show the k-step r-squared performance, which again outperforms filtered objectives as well as a variational inference technique for linear dynamics on top of nonlinear emissions. So as takeaways, our method consistently outperforms filtered objectives, learns nonlinear and transition and emission functions from partially observable systems, higher dimensional systems, or chaotic systems, augments the support of the backward proposal distribution and boosts particle diversity. Implementation and data sets for experiments can be found online. Special thanks to Christian Naseeth and Dan Hernandez.